Okay, so bond enthalpy. When you break a bond, that takes energy. That is an endothermic process. When you make a bond, energy is released. That's an exothermic process. They're equivalent. So breaking a bond and making a bond, the same bond, either absorbs or releases the same amount of energy, it's just opposite signs. So whenever we're talking about these bond dissociation energies, we're talking about breaking carbon-hydrogen bonds. So if we have CH4, breaking the first bond, the first carbon-hydrogen bond, that requires 440 kilojoules of energy. Then you have CH3 and a free hydrogen. Breaking the second one requires more energy, 460 kilojoules of energy. Breaking another bond is 420 kilojoules of energy. And then breaking the last one, the CH bond by itself, is the least amount, 340 kilojoules of energy. The energy required to break these bonds is related to electron repulsion, is related to the shape of the molecule. So in the beginning, we have that tetrahedral shape. There is some electron repulsion, but the atoms are still kind of in this pyramidal shape, and it takes 440 kilojoules of energy. Once I remove one of them, it's trigonal planar, and there is not a lot of electron repulsion. Those hydrogens are very far apart, right? It's trigonal planar. When they're very far apart like that, it requires more energy to pull them apart because we don't have hardly any repulsion at all. CH2 then becomes linear, so we see that line. Because of that, it's 420. There's an intermediate amount of repulsion. And then just the plain old CH bond has quite a bit of repulsion because it's just the one carbon with its electrons pushing the hydrogen, and you have 340 kilojoules of energy there. Questions about that?
So, if we ever do a problem with this, will it give us the bond association?
It will always give you bond association energies. You do not have to memorize those at all. It will give you the information you need. Memorization in AP Chemistry is fairly minimal. Okay. So let's keep going. Calculate the energy change of the reaction below. So we have CH3, CH double bond CH2. Going to this. Can you see that? That's our reaction. So the question is, calculate the energy change for this reaction. You have two options. Anytime you're asked to do this, you'll always be given bond association energies that you need. But your options are to break every single bond and make every single bond, or only break the required bonds to do the rearranging. That's what I would suggest. That's easier. That's what I'm going to do. But if you need to break all the bonds, you can. So let's look here. None of these bonds need broken. That doesn't change at all, right? Here, we need to break this bond, right? So we're going to break a CC double bond, and that requires 612 kilojoules of energy. Per mole. So if I had a whole mole of CC double bonds, it would take a mole, that many kilojoules per mole. Okay? And then I also need to break my HH apart, right? And that requires 436 kilojoules per mole. I put positive signs in front of them on purpose. Breaking bonds is endothermic. Positive means you're putting energy in. Endothermic process. Okay, over here, we need to make, so we broke this. I need to make a CC single bond. I need to make a CH bond using this. So this comes here.
Is that right?
Yeah. Thank you. And I need to make this CH single bond. This one. And when I make those bonds, energy is released. So a CC single bond, we're going to call that number 1, is negative 348, energy released. And then these are the same, two of them. A CH single bond is 412. Okay, so if I add all those up, my overall energy change and what this tells me is when that reaction goes, this one, in the end, I have a net loss of 124 kilojoules per mole. And that's probably per mole of this, per mole of reaction, basically. This is an exothermic reaction overall. Energy is released. This much energy for every mole. Okay. Enthalpy. All substances have so much heat content, energy that they're able to release. That means that whenever you form the bonds, energy is released. All things have that much. Opposite of that, all things have a certain amount of energy required to break them down. Those are equivalent. Whenever we're talking about reactions, we're talking about how much energy is possessed in the reactants and how much energy is in the products. Reactants are positive. We're breaking those, right? You have to break down the reactants to form the products. Products are negative because you're making bonds in the products. You'll often see this equation, the enthalpy of formation of the products minus the enthalpy of the formation of the reactants. That's fine, but that's confusing. What I want you to do is I want you to put positive signs on the reactants and subtract the products because you're breaking and making. You'll always get the right answer. Just pay attention to bonds broken and bonds formed. Enthalpies of formation is the energy released when that thing is formed. They're always going to be positive. Formations. Enthalpy of formation. Energy released when something's made. When we make things, energy is released. When we break things, energy goes in. So, H of F is enthalpy of formation. And this is the energy released when the thing is formed. Endothermic reactions, the products have more energy, greater enthalpy, than the reactants. That's endothermic. Energy goes in. Does that make sense? The products have higher enthalpy than the reactants. Exothermic reactions, opposite. The reactants have more energy or enthalpy than the products. Energy has to be given off, released. And then this is where we talk about the system and the surroundings. I've already talked a lot about this. In an endothermic process, the system takes energy from the surroundings, right? In an exothermic reaction, the system gives energy to the surroundings. And in our cases, the system is the tiny little reaction particles, the atoms and molecules that are colliding. The surroundings are usually the water they're in, because they're usually aqueous solutions. In some cases, like certain combustions and things like that, the surroundings could be air, the air around it, changing temperature. But most of the time we're measuring temperature of water, and that is our surroundings. Alright, let's do this example and then we're done for today. We're not done for today. Let's keep going. We're going to run out of time. Enthalpy of formation, write this down, this is important. Standard enthalpy of formation is the enthalpy change when 1 mole of substance is formed from its elements. So here, we're forming C2H5OH. And when I say enthalpy of formation, I mean literally from the elements. It could be diatomic, but otherwise it's a single element. So carbon is a single element. It's not diatomic, so we just put 2 carbons. Plus, hydrogen is diatomic. There are 6 of them, so 3 H2s. Oxygen, and there's a single oxygen, but it's diatomic, so we need half of an O2. And this is a standard enthalpy of formation. Delta H, this not, the 0 up here, means it's standard temperature and pressure, and it's negative 279 kilojoules per mole. What that means is when I form 1 mole of this from its individual elements or diatomics, if that's the case, 279 kilojoules of energy is released. Released because it's negative. Exothermic. This is something that you look up in a table or a book. You don't have to memorize this. You have to know how to write these reactions, but to look up the value, you just have to look it up. But you have to understand enthalpy of formation means from its individual elements. All right, the standard enthalpy of formation of CH3Br. How would we write that reaction? Carbon plus H2, but I need 3 hydrogens. How am I going to get 3 hydrogens if it's diatomic? 3 halves of an H2 plus half of a Br2. It's diatomic. That's an enthalpy of formation reaction. Number 4 says all elements are assigned a value of enthalpy of standard enthalpy formation equal to 0. Why? If I'm making carbon from carbon, is that going to require an energy? Does that take energy? Bonds broken, bonds formed, anything like that? No, that's why. It's 0. There's no change. Enthalpy of formation. Okay, that's it for today.